So in this video, we're going to look at the meaning of the definite integral and how to approximate it. So for the derivative, we said that the derivative means the slope of the tangent line or the slope at a specific point on a curve. So what is the geometric interpretation of an integral? So we have something called the definite integral, and the definite integral, what it does is it puts bounds on the integral, and these bounds are x values. A is like the starting x value that we're looking at, and B is the ending x value. So on this graph, like here's my A, here's my B. And if we're saying find the integral of f of x dx, when we put the bounds on, it's called a definite integral. And the definite integral is interpreted as the net area between the x-axis and a function between x equals a, that lower bound, and x equals b, that upper bound. So if our curve is completely above the x-axis, the net area is just the area under this curve. And we are going to find it first with approximations, and then we'll talk about how to find it exactly. But if it's called net area because if our curve is below the x-axis, we consider that area negative. And when you talk about area in general, we always say area is positive, but net area is not. So net area considers any of the regions between the curve and the x-axis above that are above the x-axis as positive, and any of the regions between the curve and the x-axis that are below the x-axis are considered negative. So if I say A is my area, the definite integral would be the negative of A, because it would be negative. And if my curve goes both above and below the x-axis, then if we're finding the definite integral in terms of areas, we split the region into both the positive area and the negative area, and then we find this area, and then we subtract this area from it. So that's what the meaning of net area is and the definite integral. So we're going to start by approximating it, and then we'll figure out how to find it exactly using our integration techniques. So we can estimate the definite integral by dividing the region into rectangles and finding the area of the rectangle. So just remember, when we're doing area of a rectangle, it's usually equal to either you can say length times width, or you can think of it as base times height, either one. So for the width of the rectangle, no matter what type we do, we find it by doing b minus a, which are those bounds on the integral, and dividing by n. N is the number of subdivisions. And then a is the starting x value, and b is the ending x value. The number of subdivisions and a and b, they have to either tell you specifically in the problem, or they write it with that integral symbol and put the a and b on there. So there's three types of approximations with rectangles, and it all is based on where we find the height of the rectangle or the length of the rectangle. And we could call this the width. We could also say this is like the base as well, if we're using this area formula, base times height. So the first one is called a right Riemann sum. Your homework will call it a right endpoint approximation. And that means the height of the rectangles are determined by the right endpoint. So let's look at an example. We want to find the area under the curve of f of x equals x cubed from x equals 1 to x equals 7 with 3 subdivisions using a right endpoint approximation. Okay, so in this case, my a is 1, that's where my x values start. My b is 7, that's where my x values end, and my n is 3 because that's the number of subdivisions. So we could find the width, or again, if we're talking about area, like the base, what the length of that is. And so we usually call that delta x, which is the change in x, which is the width of the rectangles. Okay, but again, you can say this is the base, or you could say this is the width. It all means the same thing. And to find that, we do the b minus a, and we divide by the number of subdivisions. So that's 6 divided by 3, which equals 2. So the width, or the base of each rectangle, is 2. Then we need to draw our curve to figure out the rest of it. So I'm going from 1 to 7. Okay, and if I do 7 cubed, it's gonna go up to 343. So I'm gonna go up by 50s. All right, so 343 is about here. 6 cubed. So I'm just graphing this function by pretty much I'm in making a table X, Y, and doing 1, 2, 3, 4, 5, 6. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, and 7 cubed, again, is 343. So I need my scale to go up to 343, and then I'm plotting these points. So this is going to be very low. 1, 1. Okay, and 0, 0 is also the start of x cubed. 2 cubed is 8. 3 cubed is, I'm just trying to 27. 4 cubed is 64. So this is very rough because I'm estimating where there's 5 cubed is 125. 6 cubed is like 216, and then 7 cubed is 343. So this is my x cubed, and if you remember, x cubed kind of looks like this, and would be the same thing over here. But I only care about through x equals 1 and x equals 7. And so what we're going to do is we are going to divide this into rectangles with the width of each rectangle as 2, because that's what I found the width to be. So I'm going to start at 1. For a width of 2, I would go to 3. So that's my first rectangle. A width of 2, then I would go to 5, and then a width of 2, I'd go to 7. And this is why it says 3 subdivisions, because I'm dividing it into 3 equal rectangles. And then when we draw our rectangles, the height is determined by what type of approximation we have. So this is a right endpoint approximation. So I'm going to go to the right endpoint, and the height of my rectangle is going to be whatever the height is at that right endpoint. So pretty much here the height is 27, because 3 cubed is 27. So this height is 27. This one, when I do 5 cubed, the height of it is 125. Okay, and that's my rectangle here. And then I'm going to do 7 cubed, and this is my rectangle here, which is 343. So the height of this rectangle is 343. And then what we're doing is we find the area of each of these rectangles and add them together. So my area in this case would be, again, we're going to use like base times height for each one. So, or length times width. So the width of each of these rectangles is 3, not 3, sorry, 2. So 2, 2, 2. And so for this first rectangle, we're going to do 2 times, again, that height, which is 27, and then plus 2 times the height of that rectangle, which is 125, plus 2 times the height of this rectangle, which is 343. And that's 990. And obviously our rectangles are above the curve. And so this is going to be an overestimate in this case. But it just gives us a starting point of what the area would be. So for the left Riemann sum, we're going to do the same thing. Again, your homework would say left endpoint approximation, but the height of the rectangles are determined by the left endpoint. Okay, so we're doing the same thing. Find the area in the curve f of x equals x cubed from 1 to 7 with 3 subdivisions. So again, my width, or if you call it your base, or again, textbooks will technically call it delta x. We do a minus b divided by that. We did this already for the other one, so it's the same thing. We draw our curve, and then again, we're going to go up by 50s. So we graphed this before, it's the same curve. So it's like 1, 1, 2, 8, 327, 464, 5, 125, 6, 216, and 7, 343. And your curve doesn't have to be perfect. It can just be a rough. It's pretty much you care about the heights. I'm starting here. I'm ending here at 7. Again, the width of all my rectangles is 2 because I'm dividing into 3 subdivisions. But when I do a left endpoint approximation, the height is going to be by the left endpoint. So the height is going to be at x equals 1, and then the height is going to be determined by x equals 3 for the second rectangle, and the height is going to be determined x equals 5. So again, we're using the y value here. 1 cubed is 1, so this height is 1. Here our 3 cubed is 27, so this height is 27. And our 5 cubed is 125. So that's the height of that rectangle. And then again, the width for all of these is 2. And so the area for this one would be, we do, again, length times width or base times height. So we would do 1 times 2 plus 27 times 2 plus 125 times 2. And that gives me 306. And so this obviously is an underestimate. There's like space between the curve and the rectangles. But again, it gives us just another approximation. Okay, then the third one is the midpoint Riemann sum, or the midpoint endpoint approximation. The height of the rectangles are determined by the midpoint. So same thing, the width is still going to be like that b minus a over n, because we're doing the same problem. Find the area under the curve of f of x equals x cubed from x equals 1 to x equals 7 with 3 subdivisions using a midpoint endpoint approximation. So again, if we hadn't done this already, we'd have to do b minus a over 3. Again, our width is 2. We're doing that same curve. And if you ever have to draw a graph, make sure you at least label, you don't have to label every tick mark, but some of it for the scale. And then I'm plotting these same points again, 1, 1, 2, 8, 3, 27, 464, 5, 125, 6, 216, and 7, 343. So again, my width in this case is 2, so we calculate it. So we're again starting at 1 and ending at 3, and then 3 to 5, and then 5 to 7. But in this case, we're going to draw the height of the rectangles at the midpoint. So that's like the halfway point between 3 and 1, which is 2. And I'm going to draw the height here. And then again, 2 cubed is 8. So the height of this rectangle I'm using is 8. This one I have 4. So the height of this rectangle I'm going to find when x equals 4. Again, I'm using this curve y equals x cubed. So 4 cubed is 64, and that's the height I'm going to use for this rectangle. And then at the midpoint between 5 and 7 is 6. So I'm finding the height of this rectangle at 6. 6 cubed again is 216. So that's the height. And then when I find the area, so when I find the area, I'm going to use those heights of the midpoint. So my area would equal, again, the width is 2. So 2 times 8 plus 2 times 64 plus 2 times that 216 to get the area. And that gives me 576. And again, this is probably of these three with this curve, this is definitely the best of the approximations. You can see there's not as much of a gap, but somewhat over at some places and then under, like here, it's missing this area, but it overestimates at this side, but that's definitely the best approximation. So that's how you do the Riemann sums. And please let me know if you have any questions.